Oh, hello, everybody. I hope that you can hear me in spite of the distance. I am in Paris, in France, and I hope you can see my slides as well. I'm going to try to present to you new data on the origin of common sense in geometry. And I'd like to propose provocatively that even the human concept of a square already trumps monkeys and machines, at least for now. That is to say, we all share a sense of what are simple shapes as humans. And as you will see, this requires language of thought that we think may be specific to humans. And this is the work of Matthias Sablemeyer, a very brilliant PhD student in the lab. So first, to boost this idea of a common sense in geometry, you just have to look at prehistory. You'll find that there are remarkable instances all over the world of cultures drawing squares, circles, spirals. This is in Lascaux Cave in the south of France, 18,000 years ago. You can clearly see a sort of rectangular figure with right angles, as well as, of course, displays of number and other figures. It is not trivial that we find such shapes. For instance, in a large-scale environment, like Stonehenge or this stone circle here, you wouldn't see the circle. You can only see it from above, but you're never above, of course. So you have to have an abstract concept of circle before you build it. And if you look at how ancient this sense of geometry is, you already find evidence from ancient sapiens 70,000 years ago in this ochre that was found in South Africa, parallel lines and equilateral triangles, zigzags that are in fact due to Homo erectus. There are already sets of parallel lines with roughly equal segments. And of course, bifaces and spheroids like these may be as early as 2 million years ago. So that means perhaps that this sense of geometry is actually dates back from the origins of humans and may perhaps even predate language itself as a communication device. So here's what I'd like to argue in my talk. I'd like to argue that behind human mathematical intuitions, such as the intuitions of geometry, there are actually two major ingredients. The first one is what I described in the number sense already some years ago, the idea that we share with many other animals evolutionarily ancient mechanisms that we inherit from evolution. That includes a sense of number, but also a sense of space and a sense of shape that together form our notion of geometry. But I'd like also to argue that there is something more. There is something quite unique to humans. There is the ability to discretize these concepts, the concepts of logic, arithmetic, geometry, to assign them symbols, and to combine those symbols recursively in a sort of mental language that allows us to create exact concepts that are complex combinations of the simple ones. And I already made this point a little bit in number sense, but especially in this newer book, How We Learn. I'd like to argue that this is really something that current machines don't do well at all, and that we need a sort of symbolic language in order to understand what humans do in these situations. So I will present you data from an extremely simple task, which is the intruder task. You are seeing 6 shapes. Can you spot the intruder? I bet you already did it, right? It's this shape at the bottom here. What we do here is we present you 5 shapes that are identical up to a rotation and a dilation, and there is one which has a deviant corner. With Matthias Sablemeyer, we designed a hierarchy of shapes that range from highly regular, such as the rectangle or the square, that have many geometrical properties of right angles, equal sides, and so on, parallelism, all the way up to a completely irregular quadrilateral that has no particular regularity whatsoever. And we made sure that all of these 11 shapes have the same sort of mean distances between the points, they're about the same size, and so on and so forth. And also the amount of displacement that we add in order to create an intruder is the same. So we always displace the bottom right vertex by a fixed amount to one of these 4 locations here. So this is another example of a display. So with this extremely simple test, we find something interesting, which we call the geometrical shape regularity effect. The finding is shown here. It is that the error rate varies enormously depending on the base shape. You can see that subjects make virtually no errors on those displays where the base shape is a rectangle or a square. But as the shape becomes more and more irregular, like this irregular quadrilateral here, subjects can make, and these are adult French subjects, can make as much as 40% errors in detecting the outlier. It becomes very difficult. This geometrical shape effect in this particular instance of the test could be explained perhaps by a strategy of just pointing to the most irregular shape, because the outlier was always more irregular than the base shape. And this would be, of course, more difficult if the base shape itself is irregular. But in a second experiment, we corrected that. We arranged for both a normal layout in which the regular shape is the base shape here, and also a swap layout where the irregular shape, the odd one, the displaced dot is in this base shape, and you have to spot the regular one. And in both of these cases, we replicate our effect. There's a beautiful organization of error rate as a function of shape regularity, completely correlates with the first experiment. You see that the R square is 97% here, and it doesn't matter whether it's swap or canonical, basically, except for a slight offset in reaction time. So we conclude that it's much easier to process, to remember, and to detect an oddball when the shape is regular, when it's a square or rectangle. And I'd like to argue this is part of the common sense of humans, because we find it all over the place. So we did several experiments. Here is one where we simply ask for subjective judgments of complexity. On a scale, can you put a cursor to decide how regular is this shape or this shape? And whether we ask about complexity or about regularity, you can see that there's a monotonic increase or monotonic decrease as a function of the ordering that we found in the earlier experiment. And once again, the subjective ratings are linearly related with an R square of 84% with the errors we found in the first experiment. We can also generalize this experiment in another way. Here, we no longer present the shape as a shape, but we present it as a sequence. You can see that there are 4 dots. I hope you see that in spite of the zoom. We successively present the 4 vertices of the shape. And on some cases, the final dot, the 4th dot, will be deviant. And you have to detect those deviants by clicking on a button. You see the error rate in this situation. We have fewer subjects here, but the effect is still very strongly present. The simpler shapes, like square and rectangle, are here on the left, and the more irregular shapes are here on the right. I think this is an important task because it prevents shape recognition by classical mechanisms, bottom-up shape recognition in inferotemporal cortex. And yet we still find this shape regularity. So it's the first indication that this is a high-level conceptual representation which is involved. Another experiment is visual search. This is a much more classical task. You just have to spot among several shapes whether there is an intruder which is present or which is absent. And we vary the number of shapes. There is an increase in reaction time and error rate as a function of the number of shapes on screen. And what is important is that, once again, the error rate increases linearly with geometrical irregularity, highly correlated with the previous experiments, but also the slope of the search increases in a similar manner. And there is always a slope. It's never 0 here. So this is important because it suggests that the effect we are talking about arises not from pre-attentive pop-out. It's not just pop-out, but it's from an attention-dependent stage whose duration depends on shape regularity. Now, most important, is this universal in all humans? With the help of CNRS researcher Serge Caparros, we went to test the Himba, pastoral people from northern Namibia with little or no access to formal education and a very reduced language for geometry. They have a few words, and typically they would use a phrase in order to say a square is an angular thing with 4 angles, for instance. So we tested them in the very same task, and once again, we found our geometrical regularity effect. The correlation now is less than perfect. You can see it's 55% R square. So I'll come back to that. There are a number of deviations from the French educated human adult pattern, but it's still highly correlated. And still, you can see that the most simpler shapes, like rectangle and square, are at the bottom here. They really have lower error rates for these simpler shapes. Another test of the dependence on education and another test of universality is we tested the French preschoolers and first graders. The preschoolers have no particular experience in geometry, at least in formal geometry. And you can see that once again, when they take the intruder test, they show this very nice geometrical regularity effect. And so, in fact, it's very similar in preschoolers and first graders. You may think that this is dependent on just the rectangle and the square, but that's not true. There's still a very nice correlation, even if we remove those 2 particular shapes. So it's a monotonic increase in errors as a function of shape regularity. You can see that the error rates raise almost to chance. Chance would be 83% here, 1 out of 6, correct. So there is really a dramatic effect of geometrical regularity in those children. So it's completely universal across humans that we have tested so far. Is it present in non-human monkeys? We were very lucky to be able to test baboons with Joël Fagot, a CNRS researcher in the south of France that is handling this magnificent facility where you have close to 30 baboons that are in semi-freedom. And at any time, the baboons can enter one of these booths, 24 hours, and take a video test. And there's a little chip on each animal that will detect in which test the animal is being tested right now, and will resume the testing for this particular animal, allowing you to collect thousands of trials in a very short time period. So we decided to train the baboons in this intruder task. Initially, we trained them with little pictures like that, where you have to click on the oddball flower, the different flower, and we trained them and tested them on many different pairs of shapes. In each of these pairs, one shape could be the outlier, and on the next trial, the other shape could be the outlier. Once they were trained on the intruder task with those pairs, we generalized to these testing pairs to make sure that they understood the intruder task. So these are their scores. The black line is the mean, and each color is a particular baboon. You can see that we have close to 20 individuals who completed this training part, and they all progressed very quickly in the training. They all could get to below 20% errors, which is very good understanding of the intruder task, given that chance is, once again, 83%. You can see that once they had learned these 10 shapes, they generalized very well to these 10 novel shapes, and they could also generalize to these very simple geometrical shapes where there is huge differences in the size and so on, just to make sure that they understood the task. Once they understood the outlier task, could they perform in our intruder task with quadrilaterals? Well, this was a remarkable surprise that, in fact, first of all, they were essentially at chance on the first trial, the first block, when we put them on this task, with quadrilaterals. But also, they were completely flat. You can see that their error rates are not better. They are not performing better with rectangle or with square as the humans do. And as they progress through the training, their performance improves. So you see the successive blocks on the top graphs here. And even after more than 8,000 trials, the baboons still remain uncorrelated or very weakly correlated with the human pattern. You can see that essentially our performance remains very flat, and it's still close to about 50% error, which is huge. They're not doing randomly, though, because if you look at the correlations across baboons, each line here is a particular baboon at a particular time in the training. You can see that they're highly intercorrelated. So what are they doing? Well, we thought, a very simple way to model this task is just to imagine that it is done by the ventral visual pathway, the inferotemporal cortex, which is very similar in humans and baboons. And so we use the cornet architecture, which is supposed to be one of the closest models to the ventral visual pathway. We also use different neural networks, such as DenseNet and ResNet, with extremely similar results. In each case, we use a pre-trained network that was trained with ImageNet. We fed it our shapes. And there are 5 different versions of the base shape, and there's one of the outlier shape. We feed each of them serially. We look at the vector patterns, and we decide that the outlier for the network is the vector which is most different from the mean of the others in a given layer. So can we model human and baboon data with this very simple oddball detection by the inferotemporal pathway? The answer is we can model the baboon data. So this is the percent errors of the baboons, and you can see it correlates very well across our different shapes with the percent errors predicted by the model of inferotemporal cortex. This is cornet using the units that correspond to IT, to the inferotemporal cortex. And you can see that the color dots match quite well on overall the shapes of the responses that are made by the baboons. In fact, you can already get some prediction out of the first layer, second layer, third layer of the model, and we think that the model is using some subtle deviations in area and perimeter that together define a particular shape. And it seems that the baboons were using something like that. They were detecting a sort of change in what was displayed to them, in the shape that was displayed to them. But notice that this model is very poor at modeling the human performance. The human performance is here, down here. And we are not able to achieve human-like performance with this CNN. Even when we retrain those convolutional neural networks, I could go to that in the question stage, we are not able to capture the human pattern. So in order to capture the human pattern, we found that we have to go to a symbolic model, a model that lists the internal properties of the shapes, such as whether it has two equal corners or two equal sides, and decides whether there is an outlier by the number of properties that differ. So the outlier is the item that differs the most from the others on this list of internal properties, just by the L1 norm. When we do this, we find that we can get a pretty good model of the human pattern. You see that there's very low error rate for the simpler shapes and quite high error rate for the complex shapes. And we use these two predictors, the symbolic model in orange and the neural network model in purple as predictors of the entire data set. And what you can see in this correlation matrix here is the neural network model predicts very well each and every baboon that got enough data here. So this is this big square of correlation here. But the neural network does not predict well the human data. And the symbolic model, on the other hand, predicts that square, which is all of the human data. In a multiple regression, where we have these as regressors, you can see that the violet bars are good predictors of the baboons, but this is the neural network model, but the orange bars are needed in order to account for the human data. Interestingly, the Himba and the preschoolers are in between. That means that there are two strategies basically to solve our task, and the Himba and the preschoolers use a mixture of these two strategies. There is an inferotemporal cortex strategy, but arguably there is also something more. There is really the need for a symbolic language that describes in a precise manner the number of sides, their equality, the number of angles, and so on. In the last few minutes of the talk, I'd like to discuss a little bit more what could be this language. In collaboration with Josh Tenenbaum, we have started with Matthias Sablemeyer to try to generate a precise actual programming language that can account for the basic geometrical shapes that are used in human cultures throughout the world. They are not just squares or rectangles, they are also circles and spirals. So we need a language that is able to generate these and also combinations of these, such as a chain of circles, for instance, as seen in this particular slide here. So in order to model that, we found that we need a minimal language, quite a simple one actually, that contains a few key primitives. It needs number. We need to be able to count and repeat a certain number of times, for instance, 4 times. We need primitives of geometry, such as going straight, turning, tracing a line. But above all, and most importantly, we need control structures that allow for nesting of structures inside each other. We need to be able to repeat a certain number of times. We need to be able to concatenate instructions, but we also need to be able to embed instructions inside another. For instance, how would you generate a square of circles? You need the embedding. So for instance, here you see the simple program for drawing a square. You can see that it consists in repeating 4 times the concatenation of tracing a line and turning by 90 degrees. Very simple. You could change this program, and if you added, for instance, the embedding of the drawing of a circle, you could draw a square of circles, and that would have minimal cost. And an interesting property of the proposal here is that shape perception is program induction. When you perceive a shape and you're a human, you don't just stick to a code that's provided by inferotemporal cortex. You actually try to reconstruct how would I draw it? Which program would I use in order to draw it? And if you perceive the simplicity of the shape, it is because you have induced the appropriate program. So I won't go into the details of what we are doing with Josh. There's a lot of very interesting work here to try to generate the minimal shapes that have the simplest possible programs. But I want to focus, to finish with a particular prediction about shape complexity. The idea is that shape complexity should be determined by the length of the shortest program capable of reproducing it. So you've seen the program for drawing a square. If you wanted to draw a random quadrilateral, you would have to have a much longer program because you would need to specify precisely the lengths and the angles of the particular sides. And in general, perceptually very rich drawings can be generated by a single instruction, repeat, concatenate, or embed, if the shape is simple enough. we notice that there is a particular prediction. There is a notion of additive laws, additive rules for complexity. For instance, imagine that you have a repeat instruction. It's just one instruction. It should essentially add a constant to the complexity. It adds one line or one instruction to the existing program. So the complexity of a program that repeats a certain shape should be the complexity of that shape plus a constant. Likewise, if you concatenate, you should have the sum of the two complexities. And even more interestingly, if you embed a shape in one another, if you do a square of circles, this should be the sum of the complexity of one and the complexity of the other, plus a constant for just the length of the instruction to embed. This is a completely generic prediction, which is true of any language of thought, not just a specific one we are proposing. So we decided to test it. We selected 5 base shapes with increasing complexities according to our program. Here they are. And then we generated little programs for repeating them, concatenating them, or embedding them. So for instance, you could have one shape next to another, or you could have a circle of circles or a circle of squares and so on and so forth. And we use all possible combinations of these 5 shapes. Now, what was the task? How do you measure shape complexity in this situation? Well, we decided to use the following task. We showed a particular pattern to the subject, such as
I just have to give you a warning that we're at time.
Oh, okay. I will stop in 1 minute.
Okay.
So we asked subjects to encode, press a bar as long as they were encoding the shape, and then lift it. Then there was a 2-second blank screen in that to select the shape among several. Okay. And well, the results are presented in a little complex manner, but I'll just guide you very quickly through it. We found our shape complexity for the elementary shape, and there's just one shape on screen, both in the encoding time on the top here and in the choice time when you have to choose this particular shape, memorized shape out of 6. But we also found that this would predict what happens in the other condition. Repeating the same shape, for instance, 4 repetitions of the same shape, is just a linear increase in the complexity, roughly speaking, as you can see here on the left. Concatenating 2 shapes consists in adding the 2 complexities. So there is an effect of the base shape on the rightmost position, and as well, as you can see on the vertical here, an effect of the leftmost shape. And there is an exception, which is when you repeat twice the same shape, and then there is a savings because you're in fact in this left condition repetition. And finally, if you embed 2 shapes, we still find a very good fit of the additivity property, additivity of the 2 complexities, so complexity of the inner shape and complexity of the outer shape. And once again, there is an interesting savings. If you embed a circle in itself, you have a circle of circles or a square of squares, there is a little savings because you're using twice the same program, presumably, although at different level. So I reach my conclusions. I think that in this domain of geometry, humans, unlike any other non-human species of primate, possess mental programs in a language of thought, which discretizes the concepts, assigns them symbols, and combines them recursively. And I would like to argue that this is a form of common sense. What is common to all humans in this situation, what we find simple and obvious, is simply the programs that are short. And this may explain, perhaps speculatively, why we have so much cross-cultural convergence in mathematics toward the same concepts. For instance, the Pascal triangle is found in China, and there's nothing to do with Pascal. We converged onto the same idea that this is a simple concept and beautiful concept. So I think the concepts of mathematics provide a notion of common sense that, for the moment at least, we have not been able to match with convolutional neural networks. I finish with this little joke. There was on the New Yorker lately, in which nicely exemplifies how humans project onto the external world. And thank you for your attention.